about performance, which is, of course, what most people are interested in. However, we do have some other tools that we want to present today, two of which I'm going to present, which are on the focus of correctness. So if we want to check if our code is actually doing everything as we think it would do, and if we are programming according to the standards of the programming models that we use. So I'm going to present two tools today. First one is going to be Archer, which is embedded into the LLVM environment ecosystem, which focuses on OpenMP. And the other one is going to be Must, which is our own tool, which focuses on MPI correctness. And I will show you both of them briefly. After that, I think Alexander is going to take over with CARM, which is another one which is performance-based, and later we're going to have something on energy efficiency. All right, let's start with Archer. We'll call it debugging with compiler-based feedback, and you're going to see why. So first of all, as a brief, okay, I actually have to be in the correct program. So as a brief motivation, we can do all sorts of nice little errors in programming languages like C or C++, which are giving us a real hard time to debug. So what we call this, if we do something that is not according to standard, it's undefined behavior. And this is just a brief list what could be undefined behavior. So if we read an uninitialized variable, or we do something with the memory after it was freed, dereferencing null pointer. But most importantly is this bottom part here, which is a data race, is also undefined behavior. So if two threads are accessing the same variable or the same memory location, and one of them is a write at least, then we have a data race. So it's not really defined what's going to happen there. And this is actually an undefined behavior according to the C standard. That means the compiler can do anything with it, which gives us a really hard time to debug this stuff. So let's give an example of undefined behavior, which is not a data race, but it's this little function. We initialize, we declare a variable result or res, but we never initialize it. And only if a is 32, it's going to be initialized. And when we return, we access uninitialized memory, which means this is undefined behavior and compilers can do anything with it. And if you plug that into Clang 17, you get this. So we just return A instantly. And if we plug it into GCC, we get this, which always returns 32. But both of these are actually correct compiler behavior. Because it was undefined behavior, compiler can do anything. And that means we can optimize we can assume as a compiler that only the defined behavior is going to happen, which is if A is 32, because then res is properly initialized. So either we just return A, which is always 32, because then it's not undefined behavior, or we return 32, because A is always 32. Both of them correct. All right, so, but debugging this kind of stuff, if it's kind of lost somewhere in a huge code base, is really hard, and therefore we need some compiler support to help us. And LLVM as well as GCC, but we're going to focus on LLVM today, offer us a couple of sanitizers. We can sanitize a lot of things. First one is called memory sanitizer. Second one, address sanitizer, undefined behavior sanitizer, which are the three that I'm not going to go into too deeply today, because Archer is implemented for the thread sanitizer, which is the one that gives us hints on data races and this kind of stuff. For Clang or ICX or any LLVM-based compiler, we can activate those sanitizers by using fsanitize in our compile line, compile command, and then equals and on whatever name would you want. So for example, if you want to activate the thread sanitizer, you're going to put fsanitize equals thread. All right. So just to give you a quick overview, I'm going to quickly skip over those slides because of the time. The memory sanitizer mostly just checks if your memory is initialized when you access it. So for example, if you have this code from the start, the memory sanitizer will give you this warning here. Careful, you're accessing a non-initialized memory. The address sanitizer checks if you are in bounds of your properly defined allocation. So if you have this kind of stuff where you initialize it or reserve some memory space, delete it, and then access it, this address sanitizer will tell you it's not allowed, it's undefined behavior. Again, you see always the fsanitize address. So it was memory for it, memory sanitizer, address for the address sanitizer. Of course, to get all these kind of nice warnings with line information, always have to put the debug symbols -G. We have the undefined behavior sanitizer, which is fsanitize undefined. So any undefined behavior that is outside of memory and addresses and data races is covered here. For example, we have an unsigned integer overflow. That is undefined behavior, should never happen, and it will tell you that. And then finally, we have the thread sanitizer. And for a thread sanitizer, we have to look a little bit deeper because this one is the one that Archer is targeting. So Archer is basically an extension of the thread sanitizer. So let's look at what data race actually is. So as I said, we have two threads accessing the same memory location, with one of them being a write without proper synchronization. For C, what proper synchronization means is we either have an atomic, which is making sure that this memory location is only accessed by one thread at once. And the other one is the synchronization, and this just says neither happens before the other. That means we don't have some kind of synchronization making that sure. OpenMP defines that a little bit differently because OpenMP has some other synchronization terms, but it essentially is the same. We have one of the threads being a write and a concurrent unordered access. It's always important, all data races in C, C++ are undefined behavior. There is no okay data race, but race conditions, on the other hand, are not undefined behavior. You can use them. Some people use them for like special behavior. Some locks are using race condition intentionally to implement performant locks, but a data race is never defined behavior. All right, let's look at such a data race. This is a small Fortran problem. Bear with me, I'm not a Fortran expert. I copied these slides from some colleague who maybe can help me if I get lost in Fortran code, but I think I can manage this one. So we have this parallel region here, and we just want to write the number of threads to the standard out, and we can see we are checking if thread ID equals 0, so only this thread with number 0 will write to the output line. However, this n threads variable, which is accessed here, is also written in the same kind of synchronization block. That means another thread, which could be thread 3, can write something here. And also they're writing the same value, but they're still writing to the same location. So this is a data race, but also thread ID, which is accessed here in this conditional, is also written by all the threads, because both of these variables are never declared private or anything. So they're shared. All threads are writing to them. That means we have a data race here. So how do we detect those kind of data races? We can use, oh, there we go, thread sanitizer. Thread sanitizer is basically instrumenting all our writes and reads and keeping track which thread is accessing those memory locations. and also tracking the synchronization points to make sure that you don't have, or to detect, not to make sure, but to detect that if you have some data races in your code. It detects some log order inversion. That means if you have an execution where a potential deadlock could happen, but it doesn't really happen, it only happens some of the executions, that is really hard to debug because you might run your program 1,000 times and it doesn't occur. And Threat Sanitizer will still give you a warning because it just keeps track of all those situations and makes sure, detects when you actually have a potential deadlock, even if you don't get it in your execution. It's pretty much available for all relevant architectures. And since LLVM 15, it's actually doing it's doing that faster. By the way, I forgot to mention, we have on the top right corner, sorry, it's left for me, but right for you. We have the potential slowdown you get when you run those sanitizers. For the other ones, you can look that up in the slides. It was about 2 to 3 most of the time. Threat Sanitizer gives you a lot of overhead because it has to do a lot of analysis to actually get those information. But since LLVM 15, it's manageable. It's not those 15 most of the time, and goes down to, let's say, 5 times speed up, slow down, not speed up. All right, how do we use this? Again, sanitize threat. Same with the others, and we have this kind of program where we have 2 threads with p threads this time. It's not OpenMP involved yet. There's a reason for that. I'll come to that in a second. And we are creating this thread which writes to the global variable 42. The other one, the main thread, is writing 43. So we have a data race between those. And Threat Sanitizer gives us this kind of output. So we have basically 2 writes here. One is writing by the main thread, one is writing by this thread T1. And we can see both of the lines. So first one was this one, the other one was this one. And we see we have a write and also another write that was happening before that without proper synchronization. It generates this warning. It tells us which thread was involved and where it was created. So this one points to this thread create. And down here, you always want to look first for the summary. It tells you on which line the data race happened, which is on line 10, which should be this one. Yeah, so put the lines here, you can see what those different outputs mean. For a large program, you might get a lot of output here. So yeah, you should be a little bit careful to just basically only maybe analyze parts of your application. If you have a really large application, the output can get really blown up really fast. But it's once you get into it, it's really easy to understand those. So what is left? So we said Threat Sanitizer is already existing. It's not Archer. So what does Archer bring us? So the problem with Threat Sanitizer only knows what C++ gives us for synchronization. So there are atomics. If there are standard threads, we're good. If there are mutexes, we're good. Threat Sanitizers will understand them. However, when it comes to OpenMP, with all those pragmas, with all the synchronization that OpenMP offers us, Threat Sanitizer will not be able to understand these synchronizations properly. And that's why Archer was developed. It started in 2014 together with 2 American institutions, the University of Utah and Lawrence Livermore National Lab. And since then, it has been actively developed and put into the LLVM runtime as well. Or not runtime, but in the LLVM's ecosystem. So it's shipped with every LLVM installation since 2000. 19, I think. I'm not sure. Maybe Joachim can correct me on that. So since LLVM 10, you have it, and it's also part of the new One API Intel ecosystem with ICX, ICPX compilers since the version 24. So recently they also adapted Archer. And Archer, what Archer does is it injects into Thread Sanitizer all those synchronizations that come from OpenMP. So if we put an OpenMP critical or an OpenMP atomic capture or whatever, these all kind of pragmas are then analyzed and injected into Thread Sanitizer. So Thread Sanitizer can give you a better analysis without giving you the false positives from data races that are actually synchronized via and avoided via OpenMP. There are a bunch of options that you can activate. So first of all, a little bit of a pitfall is that Ubuntu, if you have an Ubuntu installation and want to use it locally, you might have installed LLVM via the packaging system there, and this creates different paths than the default path that this was developed for, and therefore libArcher will not be found and will never be injected, even though you think it would. It will never be injected into your thread sanitizer. So whenever you run it on a system that you don't know yet, just activate Archer options equal verbose equals 1. That gives you a print at the start of the application which says Archer detected OpenMP. Pragma's, I don't know what the exact, we will see it later in the hands-on, but Pragma, it detected some OpenMP runtime directives and will inject the synchronizations to Thread Sanitizer, and you can be sure that Archer is running. There is some issue that Archer gives a little bit of more overhead for 5 or more threads, which is unfortunate, but currently still the case. Okay, what you can do is there's a bunch of options. So verbose gives you this little print about the Archer status I talked about. So it basically tells you if Archer is running. The default is 0. I forgot to mention what the default is, but you might be able to tell from the wording. Second one is to enable Archer. This is usually on, so by default it's 1, so you don't really need that even except if you really want to deactivate Archer for some reason by hand. Serial code can be ignored, so basically if you have an OpenMP program and there's serial code, then there's a parallel region, and then there's serial code again, and Archer should not run along with the serial code because there can't be a data race if we have got multiple threads. You can put that in. And also, Archer keeps track of all the dependencies between paths in OpenMP, and there's this all memory dependency, which is really expensive to analyze. So by default, this is going to be off. But if you have all memory dependencies in your code and you want them to have been to be analyzed, you can put this to 1 to enable this analysis, but this will increase your overhead again. Also, you really want to put this T-sign options ignore instrumented modules equals 1, which turns off Thread Sanitizer for all the modules that are not compiled with fsanitize thread. So for example, the OpenMP runtime will not be actually analyzed by Thread Sanitizer, which would be the case if you don't put this option. And some OpenMP runtimes have some data races actually, and Thread Sanitizer will report them and will just cluster your output and also increase your overhead.
One comment, it's not the case that the runtimes have a data race. The problem is that the analysis has a limited view on
Yes.
these non-instrumented modules because only some functions are then instrumented, and so the reports there are false positives typically.
Yeah. All right. Some quick words about Fortran. So Fortran is supported, no problem, with the latest Intel Fortran compilers. So IFX X, but you might still use some older GFortran, or you might use GFortran for your code. In that case, you have to do some trick to actually get thread sanitizer working, or any sanitizer basically. This is because you want to use the LLVM OpenMP runtime and not the GNU runtime to actually get these sanitizers working. So you compile your code still with fsanitize thread with gfortran, but then you actually compile your F90 your object files with Clang and use Clang to get the OpenMP runtime from LLVM. Right. Okay, so I've prepared a little hands-on on Archer. So if you want to follow along, it's under this path that I put here. Again, under exercises, we need a compiler that is, able to, that has Archer, which in our case will be the Intel compiler 24 or higher. I just load the newest one that's available on Mare Nostrum 5. That one has Archer with it, shipped with it, and then we can compile some code and run it. So I'm going to switch to the console. Okay, that was the wrong one. All right, so we are in the exercises tab. Go to Archer. There is this primomp.c. If we look at primomp.c, you get some output. Maybe not. Okay. Well, I think GPFS is doing a thing.
Yes.
I'm just gonna cat it.
Hiccup.
All right, so we are basically just checking between 0 or 2 and n how many prime numbers there are. We have this primes array, which contains the actual prime numbers in the end, and we have the function isPrime, which checks by looping over all previous or possible divisors from 2 to square root of the value, and checks if they're a divisor, and then flags the prime if it's a prime, basically. And we have 2 data races here, which we want to find with Archer. So let's first load the Intel compiler that I was talking about. I think that was 25.2. And then let's compile this. So first we need debug flags to actually get some line output. And then we have fsanitize equals thread, and maybe some optimization so the code runs fast. And then we want to compile this. And now, if we'll go back to the slides, okay, so maybe we can compile it without fsanitize thread first, so we can see the data race.
But you want to compile it with OpenMP flag.
Oh yeah, of course. Thank you. Yeah, I can also use QOpenMP, I guess, to get the inter runtime. Apparently that was too much for GPFS. All right. All right, so we have our executable. And if we execute this, it tells us between 2 and what is that? 1 million. There are 78,000 prime numbers. And if we execute that again, of course, that's a different number, but you may know mathematics. That shouldn't be the case. So there's something wrong here. So let's compile this with the fsanitize thread. Flag. And then we want to add some other options. So the first one is going to be Archer verbose. I don't know why I put enabled, or enable should be active anyway, but let's put verbose there. And the other one is going to be OMP tool libraries equals libarcher.so, which is our Archer library, which should be in our library path, so this should work. And now we run it and we get some output. So we can see multiple outputs of the same data arrays because it ran a couple of times before it stopped. And we can see there are basically two data arrays. The first one is in line 44 and the other one is in line 22. And we have multiple outputs of this data arrays. So let's look at these lines. So we go back to Vim, hopefully. Yes, nice. All right, so where am I? So the first one was this one in line 44. We see that total plus plus is happening completely parallel on a shared variable, which is total. So that is our first data arrays. We have two threads accessing in the same line this total plus plus. So there's undefined behavior here. And the second one was in line 25, I think, which was this data arrays here, writing on p flag of v, which might be, is that a data arrays? No, shouldn't be a data arrays.
So if you look at the output, then what thread sanitizer reports there is a race between the axes in line 22 and 25.
Yes.
So in this case, and wait a moment before going into the editor. So in this case, it's a race between axes in two different lines. For the other race, in line 44, after the colon, there's that's the column 29. And I think if you scroll through the output, there should be another report about 44 and a different column,
25, yes.
95. So column 25 and what was the other one? 30.
29.
29. So these are actually two different data races in the same line.
So this line down here has two data arrays,
Right,
one on primes and one on the total variable.
right. So and what is reported is actually the last column of the plus plus, and then the other one is a equal sign. is the assignment. And so if two threads accidentally have the same result for the total plus plus, then they also write to the same element of the primes array, and that's a data race for the equal in this line. And then for the other data race, 22, 25, that's writing the value down there and then checking for the value in the if.
Yep. Third time somewhere.
And I think in the interest of time,
Yep.
people can solve that as homework or in the practice time, and you probably go on with the other tool.
Yep. All right. Do you have any questions on Archer so far? Right. So we covered OpenMP. Let's switch to the other tool that I want to present, which is MUST. MUST focuses mainly on MPI correctness. However, we have some combination of the both. That's why we have that it says MPI plus OpenMP, but it MUST mainly is a checker that brings MPI into the correctness checking. All right, let's look at this code. This is completely wrong code. You definitely see that immediately, right? So there's a couple of issues in this code. We are missing a MPI init. We're missing an MPI finalize. We're using Fortran MPI integer instead of the C MPI int. We have a mismatch between this type and this type. So we have a mismatch between the receive and the send. We have a mismatch between, no, there's no mismatch, but we have a deadlock because we're calling a blocking receive before the blocking send. So every thread is, every rank is going to hang in this receive. Then also, we're going to get out of bounds here if we are trying to receive from rank size. So if rank is 0, we're going to have an out of bounds here, basically trying to send and receive from and to a rank that is not existent. So you see that there's a couple of issues in this code, and of course it's easy to see that here, but you might have done something wrong in your codes, which is way larger. So we need tools again to find that. And what MUST is for, we compile this code, we run this code along with MUST, and MUST will do some analysis, spawn some more processes to handle some data and analysis to get basically the same we did for threading, for thread sanitizer, for MPI. So we check if there are mismatches between MPI communication. We check if there's the types are matching. We check if there are potential deadlocks and stuff like that. So MPI programming is somewhat error prone because we might run into errors that we can't see immediately. So there's a bunch of errors that we can do. If a code does not compile, of course, the error is very obvious. But if the code compiles and gives us a wrong result, that's also might be obvious, but there are more subtle errors as you go on. So sometimes the error will just not manifest and we will not see it, and maybe it just manifests on a special system. And yeah, basically, if the application finishes with the correct result, it's really hard to see that you might have an error. So running it with a tool might help you with that. So what does the MUST output look? So I'm going to show you what the actual result of MUST is. So before we use it, we get an HTML output out of MUST, which is a little file that you can open with your browser. And this contains a list of errors. So hopefully in your case, there will just be one bullet point, which is no errors found. But you might run into some of the errors. And for example, to look at our deadlock sample again between the receive and then the send, we get some kind of output where it says, okay, which ranks were involved? What is it? So there are errors and warnings. And then there's going to be a message. And if we click on that little list item, it expands. And then you get a little bit of more text here, which is basically the description, which tells you what exactly went wrong. So we saw, okay, that can cause a deadlock. And then also it tells you where exactly this deadlock is going to happen. And it tells you the line, what exactly the points would be if that deadlock occurs, where the ranks would hang. So basically here you can see on rank 0, we are sitting in line 15, and on rank 3, we are also sitting in line 15, and we are sitting in a deadlock because can't continue. So when you click on this deadlock view here, we also generate a little graphical representation of how this deadlock looks. So basically rank 2 and rank 0 and rank 3 are both sitting in this MPI receive, waiting on each other, and or waiting on rank 1, which also was in a receive. And we have our communicator and our tags with it. And finally, we also get a simple call stack, which tells us in which function we actually sit. So this is the things that must will tell you for an error. So it tells you who was involved, what the error was, where the error occurred, and some details. And it also, if you keep on clicking deeper into the HTML file, you will see some more information and some graphical representation. But deadlocks are not the only thing that Must can detect. So another thing would be if we have issues with our buffer sizes, with the transfers, and with our types. So in this case, we had the issue that, what was the issue? We had a type mismatch between a send and a receive. And again, it will tell you which ranks were involved. This is an error. This is actually a problem. And the description from which send it actually happened, and what, again, where the lines that each rank was in. So in this case, you can see there are a couple of more errors here that we had in our program. And if you click on one of them, it expands basically to this top view here. Again, there's a great graphical representation of the data types involved to give you a little bit more insight if you click on the message. We also have race conditions that are covered here. So so we had the send with the type, and we are receiving on. Sorry, I'm pretty methodological. Joachim, can you help me real quick?
Yeah, so the interesting part here is that for the MPI call on the right, so for the I receive, you don't see the absolute address, because then it would be tedious action to compare what is the distance between those. But in this case, they have an offset of 0, so they are so both buffer arguments are accessing the same element of the buffer. And if you go back to the original code, to the initial example, right? So what we did here, so we cannot detect this error as long as the application deadlocks in the receive. And so for the error message that we saw at the end, we already fixed the data the deadlock by using iReceive, and that means that the receive is executed concurrently with the send, and then the receive and the send both access the same buffer without an offset, and so the receive tries to write into the buffer, the send tries to read a value from the buffer, and that's the race that is reported there.
Yeah. Right. So the next one, what we report is if we have leaks of user-defined objects. So if you create a type or a communicator or MPI groups, for example, and you don't free them when finalize is called, then you will have a leak. So according to the MPI standard, this is a bad behavior. And we report this. And also we report if there's any pending communication that was not received. So for example, here we have first a leak of a user-defined object, which was this type contiguous, which was never freed. If you don't free it, it's technically leaked when we call MPI finalize. So this is reported. And the second one that we report here is that there's an unfinished communication when finalized is called. So basically, we never waited for the iReceive, which means the iReceive is not finished or could be not finished when we call finalize, which is a pending communication, which is without the synchronization. It's also something that we report in must. And then finally, once you fix all the errors, you get a message like this, which you're happy about, which is the green information. You don't have any errors in your MPI code. All right, so how do we use must? We don't need to recompile or anything with for the use of must. However, we need debug flags to actually get line information. And then we simply replace the MPI run with a must run. So we compile our code here with -g, and then we replace the MPI run with a must run, and give how many processes we want and execute the application. This --must MPI exec is a parameter that you can use to define what exactly the MPI run command would be. So here we have MPI exec MPI run. So we actually want to use the MPI run. So you might want to use srun if you have if you're using a Slurm batch system, or if you're some other MPI commands that are not covered here. But I don't think there's many more. And what you have to keep in mind is that must run will always spawn more processes that you requested because it needs to do the analysis. So if you just put must run here, you activate the so-called centralized analysis, which means there's only one additional process spawned. So if we do must run -n4, we'll actually spawn 5 processes, because one is doing the analysis and 4 are doing the actual run. You have to keep that in mind when you allocate your resources. So if you want to use must with, for example, 4 cores with an MPI run, you allocate 4 cores, and then do must run, you actually get 5. So you have some oversubscription then. So keep that in mind and just reserve 5 cores for 4 and 4 process run. You want to actually put tasks 5, for example, in your Slurm batch script. We have some more options that I'm going to show in a bit. But the default configurations allows the application to actually crash. So if you have severe errors that crash the application, that is covered. Must will not crash and still generate the output. However, this means that must can only do the analysis a little bit slower than if we assume that the application never crashes. So you can tell must that the application is not crashing, but more on that later. All right. So any questions on the basic usage of must and what must are scaling a little bit more than four to a little bit more than four processes? When you have more than 10 processes, the analysis for one process gets a little bit hard and a little bit resource intensive. And to basically spread out and parallelize the whole analysis part as well, we offer this tree-like fashion where you can have the tool processes organized in this tree to get a distributed analysis. To do that, you can use this -- must fan in 8, which basically is a factor for must how many tool processes are one tool process, how many application processes are handled by one tool process. So that's the correct thing. But to actually get the amount of processes, you need to put that -- must info, which tells you how many actual processes will be spawned if you use that fan in parameter. So for example, if you have 8 processes, Joachim, do you know how many total processes will be spawned if you use fan in 8?
So with 40 application processes in this command, then we will have 46 total processes, because for the 40 we need 5 processes in this first level, and then they will be then we have this additional process at the bottom.
Yeah. So eight application processes are handled by one must process, and then all the 5 must processes are handled by one additional must process, which is doing the centralized analysis again, the centralized parts. All right, so the workflow here would be first execute this one to get how many, allocate enough resources to get your analysis, and then run this one to actually get it. Again, I told you there's some assumptions that we can do for crashing. So if you think the application might crash and you have not enough processes in your analysis to actually have a performance problem here, you can just use no parameter, just use must run. Then we also have this part where we have both. So the application never crashes and we have a lot of processes. In that case, you can use fan in some number. But there are the 2 other cases where, for example, the application never crashes, but we have not enough processes to make use of fan in. We can use -- no crash, which gives us a little bit faster analysis. And then also when the application might crash, but you still want to have the distributed analysis, there's another process, a flag which is called node size. Node size is basically, can you explain node size real quick, Joachim? I'm not too deep into that.
So the name is a bit confusing. It comes from times when nodes were actually just 4, 8, or 16 processes. Now we have nodes with 69 cores or something like that. And so the guarantee that you provide is that the number of processes you put there is a divisor of a shared memory node. So must will split the overall processes into these chunks and assume that all the slices that it gets run on the same shared memory. So node size must be a divisor of the ranks on a shared memory node.
All right. So also we provide multi-threading support. So you might know MPI does not only offer single-threaded, but there's thread-aware MPI. Usually by default we only support thread funneled, so only one of the MPI of the threads per MPI rank is communicating. But there's this -- hybrid parameter that you can use to support thread multiple. Some MPI libraries have some additional flags that you need to set, but this is really implementation specific. And again, you can use must info to see how many resources you actually need. We offer stack traces. Stack traces are collected by the backward CPP library. There are three options for a stack trace. We can actually get no stack traces addressed to line, which just gives you basically the last one, or backward, which gives us the whole stack trace. However, stack traces are a little bit expensive, so you might want to think if you want to have stack traces or just the errors with address to line might be enough for you. Also, we offer filter files. If you want to have the analysis only run on specific files of your application, you can use the filter files. That way you can filter files, and also you can filter error kinds. So if you just are interested in, let's say, memory or leaks, you can filter all other out, or if you just want to filter out some kind of error, so you say, I don't care if I have a communicator still allocated when MPI finalize is called, don't report these errors. You can just give like the message type, which would be must error leak data type, and a star, so it's ignored for every file. With -- must filter file, you can actually put filter file. Joachim, you wanted to add something on the CI here?
Yeah, so this option is especially useful if you want to run must in your CI for the application, because eventually you want to get a green flag for the pipeline, and if you have some errors that you want to ignore that you will never fix, or must also report some not errors but warnings that arguments might be zero, and usually they are harmless, then you can just suppress the reporting after you check that it's okay, and get the green flag in the pipeline.
All right, finally, some more options that are available. So first of all, we have a help, of course. We can -- must help to get a little bit of a manual. Then we have the output formats. So I told you the standard output is HTML, which gives you this HTML file that you can browse. But if you don't have a browser available, or you are more interested or want to parse it automatically in your CI, for example, there's also a JSON output and also a human readable textual output on the standard out. We also have some options that you can use with the parallel debugger DDT, which Joachim, can you help me again on that? I think I've never used must with DDT.
So the problem to use must with DDT is that most of the time we spot the issue later than it actually arises, and so with these two flags, so we first run a record run where we identify the issues, and then in a replay, we stop the execution at a point where the error occurred, and then there is also integration into DDT, so that DDT will actually show you what the issue was at that point that must report.
Thank you. All right, finally, I told you about Archer, and now I told you about Must, or we, better. You can actually combine those both. So you use Archer just as normal. You compile with a sanitized thread, and you activate this option must tsan. And then you need to put a helper library to actually integrate the output from thread sanitizer into your must report. So it actually gets put into the HTML file. And when you do those kind of steps, again, you need to make sure that your MPI compiler, so the MPI compiler wrapper is actually calling some LLVM-based compiler. So you want to set for OpenMPI the OMPCC, or for Intel MPI the IMPICC, or for MPICH it's MPICH or CXX to some LLVM-based compiler. You do all those kind of stuff, and then you get output like this, which also includes the thread sanitizer output that we saw earlier into your HTML report. So that combines both of these tools into one output, which is convenient to analyze.
The advantage of integrating this into the HTML file is that at the top left you see 0 to 7. And that means you would get for all the 8 processes, thread sanitizer would create the output, and all that would go to the command line. And so you can execute this without the last step shown on the previous slide. So if you execute without this helper library, the output will not be included to the HTML, but it will pop up on the command line. And as you probably know from application output coming from multiple processes, the output is usually interleaved, and so you will get completely scattered output, but you can work with that. So if the integrating this helper library doesn't work, you can still use this to detect errors.
Right. At this point, I had a little hands-on planned, but I'm out of time now, so I would move that hands-on to maybe after the break, or whenever we do the.
Then we have the hands-on part.
Yes. Okay.
Yeah.
And
So
You can use that. Yep.
And what the hands-on basically does is it analyzes the example we had on the first slide, goes through the errors, and you can fix them step by step, and then get all the intermediate outputs that were basically also already shown at the beginning of the MAST presentation.
Yep. So you can also throw must immediately on your own codes on the hands-on if you want. All right, then I'm going to stop the presentation. Any other questions that we have not answered or are not clear?
Share my screen first.
So I will mute the.
Okay. I hope you see my share, right?
Yes, all perfect.
Okay, perfect. So I'm Alexander Ilic, and I'm coming from Ineshkide. And in the part of this presentation, we're going to cover the roofline tool, or the CARM tool that is developed at our research institute. And I'm presenting this on behalf of our research team that you have also in the slides here. So I'm going to keep it high level, less technical, so that I cover the most important part and get us set up for using the tool. So I'm starting with the biggest motivation behind using the roofline tool, and why we actually aim at developing it is, as we have learned in the previous days here, is, HPC systems tend to be very complex and heterogeneous, which makes them very hard to model and very hard to optimize applications on them. So CARM can come as, or cache-aware roofline model can come as one potential solution, which does not actually aim at give you all possible answers. Neither it aims to be very detailed. It is actually aimed to give you a high-level overview or give you a first insight of where you should start in order to detect what are your bottlenecks and what you can do about it. It also gives you an idea of how far away you are with the optimization in what respects the maximum of reaching the maximums of your architecture. And like this, you can probably estimate the optimization effort that you have to put in order to further improve the performance of your codes. So when it comes to that one, the roofline tends to be like in the previous year, very fancy tool in a sense that is like you can have many different papers, both in the architecture and application optimization that to a certain extent relies on the roofline modeling. And the reason for that is simply because it's very easy to understand and it gives more or less fairly accurate performance overview of the maximums of the architecture. And it may guide you in certain regions of what kind of optimizations you can implement. A cache-aware roofline model is originally supported only by Intel Advisor tool, which is, as you know, commercial tool, and we work for several years with Intel Advisor folks in order to deliver this experience. However, having it completely vendor locked is something that actually it's not a good thing, and this is some part that we would like to tackle by proposing our own in-house CARM tool. So before we go to that part, I would like actually to cover first some pretty basics regarding the cache-aware roofline model, why it is different than the original one, and how we can actually use it. So as you may know, is the roofline model has actually those two axes here, which is the Y and which depicts the performance, and it's in the log scale. And on the X, we have arithmetic intensity, which is expressed in the flops per byte. You can think of it as the total amount of flops that in your code or certain part of the loops that you have performed per byte that you transfer. Obviously, you would like to have a lot more flops per byte to transfer because it will put you to the compute bound region, but obviously that also depends on the code that you are running. And not so great situation is what we typically have is that you perform not so many flops around so many bytes that you transfer across your hierarchy. So when you look to the model is actually model of the architecture and not the application. And when you look to the model itself, it actually has several sloped lines or diagonal lines in the cache-aware roofline model, which depicts you the maximum performance that you can get from your architecture once you are traversing different hierarchy levels. So obviously, if your data is all in the DRAM and you're deeply memory bound, then this line will actually depict you the maximum performance you can get. As you go there and then you exploit more locality in your caches, the architecture will reveal more performance up to the maximum that you can get for L1. Of course, the full maximum performance you can only get once you are exercising only compute units. And this is represented with this horizontal blue roof, which represents the maximum throughput of your ALUs or arithmetic operations. When you have all of that together, actually there are three regions in the roofline model that are of interest that you look when you are interpreting your application. The first one is the memory bound region, where if you plot your application, which is just a dot in the model, so again, lines are architecture maximums and dots are your application. So if your application is limited just by the diagonal slopes, then we will say that you are in the memory bound region. Furthermore, if you are limited in the blue region, which is just by the horizontal line, then you will have a compute bound region, but you can also be in between, which is a mixed region. And this is a region that is a little bit harder to optimize. So once you detect a region where your application lies, from there, you can pinpoint more or less the optimization techniques that you should apply. For example, this dot here that we have points the application where it's completely memory bound. So it means that your optimization effort should go more towards the improving the access pattern, having more use of the data, or rethinking about your data accesses. If you're in the blue part here, as we can see here, you should actually more focus on the compute-oriented optimizations, which can be vectorized in your code, reducing the impact of log latest instructions, or even parallelize it if your code is not. If you're in the mixed region, this is the region where you actually have impact of both. So it means in order to reach the maximum of architecture when you're optimizing your application, here you would need to apply both memory and compute bound region. What is specific property of the cache-aware offline model, which does not exist in the other types of offline model, is that once you optimize the application, you don't expect really to change a lot in arithmetic intensity, because that is intrinsic property of your application. What you expect is that when you improve your code, that your execution time will reduce, and as your execution time reduces, your performance will increase. So it means you will expect that when you optimize your application, that the point will actually start moving vertically up to the maximum roof. Of course, how much of that you can exploit in reality depends on your code and many different factors, as you already know. So let's go back how we actually construct the cache-aware offline model. To do that, we need a set of micro benchmarks for both memory part and compute part. And that is something that we provide within a tool that are completely in-house micro benchmarks that are automatically generated for you. So why did we need a tool? So in fact, almost every major vendor nowadays has some roofline applied, which are supported to different extents. For example, Intel went really far away with the roofline support in Intel Advisor. They officially support cache-aware offline model, and in terms of the application analysis, they rely to the dynamic binary instrumentation, or DBI. Of course, as you know, it's not open source. The same applies to the IMD UProv, which actually applies the original offline model and use counters for application profiling. Both of them are not open source and they're vendor locked, so it's like they typically work only for x86 architectures. If you look to something that we have in the open source space, which is Empirical Roofline Toolkit, or ERT, they support both Intel and AMD, but the way how they do the construction of the roofline is mostly based on application benchmarks, which actually do not give fairly accurate way of representing the maximums. And they don't give any support for application analysis, which means you may be able to construct the roofline, but then you have to do application analysis on your own. Having that in mind, the tool that we are proposing, or that we developed, the CARM tool, actually covers all major vendors and NICEs in terms of the CPU department, which is Intel, AMD, ARM, and RISC-V. It fully supports CARM benchmarks that are embedded in the tool, which means that the model automatically gets constructed, and we support both types of application analysis, which are counter-based, based on PMU, and based on dynamic binary instrumentation. And it's fully open source. You can find it on our GitHub, which I will share very soon. So when you focus directly on each of the supported architectures that we have, so we support also all possible ISIS extensions that you get, which, for example, for SIMD in Intel goes from Scalar SSE AVX2 to AVX512, also for AMD. For ARM, we support Neon and SVE. And for RISC-V, we are also supporting RVV07 and 1.0 specifications. So I will now briefly give a high-level overview of the CARM tool, its recent extension to the GPUs, and I will briefly touch the integrations that we have with different HPC tools, centers, and co-design activities. So in what concerns the CARM tool, in a high-level overview, we provide two different types of interfaces. We have command line interface, which is kind of geek approach, and it's typically used if you would like to integrate some roofline facilities in your own tool, or if you want just to crunch your data in a completely different way. We also provide GUI, which is a graphical user interface in which you can configure your benchmarks, which allows very big customization in terms of the roofline view, and also it allows you to specify your application and profile it. And then upon that, there is a certain facility in automatic micro benchmarking and application analysis. So in terms of the high-level overview, it's like those are, if you go there and then just check out our tool from the GitHub, this is more or less what you will see in terms of its organization. I'm not going to bother entering into each of those files, but I will just give you more or less what are the modules that are giving the full functionality and how can be used. If we focus on the first one, which is graphical user interface, in this case, we have obviously the way to represent roof lines once your architecture is already benchmarked. And as for now, we provide up to 2 roof lines that can be represented in parallel. They can represent the same machine with different ICE extensions or different tests. It allows parameterization across different ICE extension, different precisions, amount of threads or cores, different ratios of load and stored operations, and a bunch of other stuff. And in the bottom here, you can also specify your application. In a sense, once you get the points, is that you can go there and then plot different loops or different tabs and visualize them in the roof lines inside. Of course, on the left-hand side, you have a configuration panel in which you can specify which kind of micro benchmarking you would like to perform in your machine in order to have custom roof lines constructed, which gives you to specify directly the sizes of the caches, or the tool can automatically detect that as well. Thread counts that you would like, what is the extension, what is precision, load store ratio, and so on. In the bottom part, you can also provide your executable file with the arguments, and then you should select the type of the analysis that you would like to do. As I mentioned, we support DBI and PMU, for which you can also specify the regions of interest. So furthermore, we now focus on the automatic benchmarking facility. In the automatic benchmarking, this is completely hidden from the end user. I'm just presenting it here just to know what happens under the hood. So as I mentioned, we provide facility to automatically detect the cache sizes, also clock frequency, and according to that, configure automatically our micro benchmarks for specific platform. So it also has a platform detection here, for example, on the right-hand side, for if it is a RISC-V RVV vector instruction, we can actually go there and then detect also what is the maximum vector length that you are supporting. Then, according to that information, we are automatically configuring and generating the assembly micro benchmarks in order to fully test your architecture. For example, here we have in this changing graph, you can see that many different tests and different flavors of the testing that are generated in assembly for different type of vector extension for Intel, ARM, or for RVV instruction sets. Then, according to that one, then we move to the last major part, which is application analysis. For application analysis, we have support PMU analysis through the PAPI high-level interface. And for that part is obviously it allows you to specify the region of interest for Intel, AMD, and ARM processors, for which you need to include your PAPI API header file, and then you have to have the region of interest with the begin and end between the for loops or whatever is the part of the code that you would like to benchmark. After that, it will automatically collect for you the required counters and allow you to plot it in the graphical user interface. When we focus on the DBI functionality, which is dynamic binary instrumentation, we support 2 tools, DynamoRio and Intel SD. Obviously, for the Intel platform, we do recommend using SD. And that one, it allows full application analysis with region of interest. Of course, this is what allows us to cover all possible platforms like Intel, AMD, ARM, and RISC-V. Although RISC-V supported DynamoRio was still experimental when we were plotting it. We also provide our own in-house determination of the regions of interest, which interface after the DBI tools, for which you just need to include a header file and then put around your loops the region of interest begin and region of interest end for our CARM analysis. Having said that, now we have a demo showing how the tool actually works in practice.
In this video, we will overview the different features of the CARM tool, starting with the graphical user interface, which can be accessed by running the results GUI.py script. You will then receive a link that you can open in your browser. Then here in the sidebar, you can configure your CARM benchmarks, associate a machine with them, select a thread count to test, an ISO extension, the precision and load store ratio, among other things. And you can also just click the Run CARM Benchmarks button to use the default settings. In the terminal, you can then consult the intermediary output of the tool, which includes the detected system information like the cache sizes and available ISOs, and the tests that will be performed. You'll also get a breakdown of the benchmarks as they finish, with various metrics such as the recorded CPU frequency, the peak bandwidth of gigaflops measured, instructions per cycle, among other things. In the sidebar, you can also run application analysis, where you can choose a machine name to associate with the execution, select the type of analysis you want to run between dynamic binary instrumentation and performance counters, and then provide the path to your executable along with any arguments that it might take. In the GUI, you can also consult the results of the CARM benchmarks and from application analysis. To do so, just select from the available machines in the dropdown, and then select from the results you have stored based on their settings. And here you can plot 2 CARM graphs at a time to compare them, and then you can also plot the results from application analysis or mixed benchmarks via this dropdown, which will then show up as dots in the plot. So to analyze your applications, you simply need to include the necessary header files for either DBI or performance counters. And then you can use their corresponding API functions to define your regions of interest. So this tool requires no knowledge of assembly, since all the micro benchmarks are automatically generated based on what you choose. As you can see, you can also launch the various types of benchmarks from the terminal, like so. And this concludes our demonstration of the different features of the CARM tool.
Okay, we also use you can also use CARM like to perform a deeper analysis of your applications, even across different architectures. For example, here we are showing an example where you can plug in the same application that is run on Intel platform and ARM platform, which is actually SPMV with reordering. And then in both of them, we can see that from the original, we get performance improvement once we reorder the data because of better locality. And since Intel, in this case, give us a higher performance, of course, the application which is involved. Of course, what we can also observe here is that there is no difference between the significant difference between the PMU and DBI profiling, which is something that is expected to see once you profile with both of them. So just to briefly touch on the extensions to the GPU, we recently worked on providing GPU support into the current tools. So we are in the final stages of that, if not completed. We have functionality tested for both CUDA cores and Tensor cores and across a full memory hierarchy, which includes shared memory, auto-cache, and global memory. And for application profiling, we use the N-side compute to profile the entire application or target individual kernels. For the AMD GPUs, now we are finalizing its usage via HIP and AMD ROC-Prof. So just to show how it is done, so similarly to the CPU microbenchmarks, we have developed the target instructions in the PTX assembly by running thousands of iterations with thousands of threads. If you go and focus specifically on the Tensor cores here, we actually have different instruction shapes for matrix multiplication to specify and different precisions that we can use. So this is kind of an excerpt of the code with a high-level view. So for example, you can have FP16 with 32-bit accumulation, BF16, and TF, and as you know, all the other guys. In terms of the efficiency of the micro benchmarks that are embedded, we were quite surprised that you achieved almost near theoretical values in the GPU. So for example, the deviation was 0.5% over the RTX 3080 and 2.5 on A100 due to the certain exceptions in terms of the support for int8, and binary precision. So in order to further validate, here you will see that we construct performance. We also have variants for power consumption and energy efficiency rooflines that I'm not going to cover in this presentation. But as we can see that with our validation, we could actually manage to uncover the maximum of the architecture even experimentally. So how we actually use the tool after, it's like we tried to profile certain GPU kernels, and for that one we focus on the ones that are the fanciest nowadays, which is using kublas and kutlas for gem kernels, and also we try to profile some convolve kernels from the cuDNN library. So what it focused in the gem, we try to actually go there and then see what are the maximums and what is the impact of different matrix sizes across different implementation and different precisions. So we use kublas on FP32 and the TF32, which runs on Tensor cores, and also kutlas TF32. We can see that there are actually 3 different implementations since they target different arithmetic intensities. And what this study actually shows is that for any of them, you need to have really decent matrix size in order to be able to explore the maximum architectures and arrive to the compute roof. The same applies even if you run FP16 over the 32-bit accumulation. However, here the difference is that if you use Tensor Core, you can get double the performance than what you get with the CUDA cores. Obviously, if you use Tensor cores, in this case, you can also get a very, very higher efficiency, which gets like in terms of the GFLOPS per joule energy efficiency, which equals to more than 80% or even 160% in the FP16 with 32-bit accumulation. Similar studies we performed for the convolve kernels. Due to the time sake, I wouldn't go into much details, but we evaluated what are the impacts of different implementations across different precisions for 3 different metrics, which is tensor dimension, filter dimension, and number of channels. What we actually show here is that there are different implementations even in CUDA libraries, and they may have actually different efficiency depending on the parameterization. Obviously, tensor dimensions and filter dimensions, if you have the higher one, it's good, but it's not the only one that allows you to exploit the maximums. For example, here what we actually show is that having much more channels will actually be the one to allow you to fully exploit the GPUs. And from this, we try to actually influence a little bit the design of different layers in terms of the neural network, such that you can, by the design, already know how much of a maximum you can exploit in the GPU architecture. In terms of the recent works, which in which they tackled the integration of the CARM tool into different HPC tool centers and co-design activities, what is specific niche that we try to cover with CARM is that it provides this kind of architecture overview, which typically we focus only on the application domain, and this is kind of a stuff that gives a little bit distinction of the roofline analysis. And because of those reasons, we have a very close collaboration and extension with many state-of-the-art tools, and some of them you had very deep coverage during this workshop, which is a part of our team at BSc. Then we work with the CODA-SIP on GPP co-design in scope of the DARE project, and with certain folks, we also work on their adaptive performance modeling tool. So in the scope of the POP3 project, it was actually one of the parts where the CARM tool was born and then being very well developed. We focus on deployment of the tool into many different supercomputers. Now we actually have it deployed only in Carolina, and we are working to port it to different parts, since we are redesigning some parts of the tools in terms of the micro benchmarking. We expect to have this happen in a few months from now. In terms of the integration with the Paraver tool, actually we support, it is integrated as a separate module, and which means you have to have CARM tool installed and Paraver, and then it will just appear from there. And you can actually go there, and then it provides the analysis via extract ACEs. It provides a full synchronization with Paraver timelines and the timestamp coloring. You can also export the metrics from the CARM tool directly in Paraver and change the different coloring scheme depending on the metrics that you see. Here, we also provide completely different interface in our CHAM hub that allows to sync with the timestamps from the Paraver and the CARM tool, and then visualize where your points here are presented in terms of the maximums of the architecture. In the scope of their project, CARM tool and CARM itself, we think about using it to influence hardware design, which that there will be a low-level architecture where support for CARM in the RISC-V based code C processor, which is able to drive the next generation HPC systems in the Europe, and we will be working closely with them in order to provide characterization and application of applications and architectures at the same time, but more from the hardware perspective, which is different kind of thing that we typically use the cache-aware roofline model for. So here we will try to actually optimize architectures from the set of target applications. Of course, the tool is fully available at our GitHub in the CHAM hub, both versions of the tool itself, as well as the integration of the Paraware. In terms of the hands-on, we didn't prepare it as for now, but we are happy to work with you offline if you're interested in using the tool. Thank you very much. If you have any questions, I'm feel to take it.
Hello, everyone. Let me introduce you energy efficiency analysis of parallel applications, how we do it in the POP Center of Excellence. So, first of all, I will start very generally about the energy efficiency. The typical equation of the energy efficiency is performance delivered per watt. So first of all, what's the performance? We need to somehow evaluate it for an application. So typically, an application may have its own way of reporting the performance. So that's the best way. If we have, for example, a lattice Boltzmann app, then there is a number of lattice updates per second. So that's the perfect way of expressing performance of the specific application, while obviously the general one is flops per second. In the most common or well-known is the Green 500 list, where they have their own metric. They have Linpack Air Max, so the peak performance of this benchmark divided by average power. So to make it general, the easiest way obviously is using the flops. So measuring the flops is first essential part of expressing application energy efficiency. To compare various runs, various architectures. So yeah. Yeah, in this slide, I have flops evaluation from a variety of instruction sets, which is especially in case of Intel CPUs important because the instruction set impacts the frequency on which the CPU is running. So here I have some quite old architectures, but this is exactly the same for the recent ones. So according to the instruction set, if you are using higher instruction set, you are using frequency. However, anyway, higher instruction sets brings you more performance. So it's obviously the best way how to improve energy efficiency is improving performance of the application. And it means using the proper vectorization of your application. So that was the performance, that one side, then now the other side, that's the energy measurement. First of all, basic introduction, what's the energy? So that's power multiplied by time, so evaluated in runtime of an application. If having a power consumption of 1 watt for 1 second, it's 1 joule. If it's for a longer duration of 1 hour, then it's 1 watt hour. So that's, in our case, typically we focus on joules. because the application energy consumption is not so high, but it only depends how long your application is running. So obviously the power consumption is not stable, it changes in time, and the power monitoring systems are sampling what's the power consumption on a specific rate of the samples. So then we may have such an power consumption timeline of an application changing in time, and obviously we must evaluate from the power samples the energy consumption as integration of that. So we have in the HPC variety of power monitoring systems, and the power monitoring system is really specific what power domain it measures. So here's an example from the Oak Ridge or Lumi, where there's the same hardware. So AMD CPUs plus AMD GPUs. So having energy measurement just of the GPUs is really GPUs, another is for CPUs. But anyway, there are parts on the board which are not monitored at all, or potentially from the power monitoring, which is not available for usual user if the rights are not escalated. So and additional, let's say, issue of the out of band power monitoring, which is the monitoring from the IPMI or the redfish implementations, is that it monitors on significantly lower sampling frequency. So let's speak about the well-known Intel RAPL. It provides 1,000 samples per second, while the IPMI at the maximum, if really is increased to what's the system is able to provide is few samples per second, typically 1 sample per second, so 1 hertz. That's you can see the difference. But in that case, the out-of-band power monitoring here monitors everything. So potentially you can combine this power monitoring to have better insight. But we do not have such rights here, so let's focus further. Yeah. Important part here, as I said, here we have variety of hardware platforms, variety of ways of monitoring the energy consumption. And in that case, it's important to know what hardware we are using for the application. So, and we're not just measuring the energy consumption, but also potentially doing some optimizations, then it's obviously critical to know what frequency is available in the machine and what impacts the frequency when running the application. So, working on the Marinstone 5, we have here the Intel Ceph CPU. So, the Intel CPUs have 2 power domains. That's a core and uncore. You can see the uncore area is pretty large, approximately 30% of the chip area. While this area has its own frequency and impacts the shared, for example, last level cache or interconnect. So more the uncore frequency impacts the memory-bound workloads, while obviously the core frequency impacts the core compute-bound workload. The importance of each frequency depends on typically on arithmetic intensity. So that's the roofline model we saw in the previous presentation. So that's the blue line here in the chart on the right side. While that's an example of an application of variety of arithmetic intensities. So what performance it reaches while how the memory bandwidth drops for that specific architecture. What are the other reasons for bounding the performance of the application? It obviously can be, for example, the communication or I/O that do not let us increase the compute boundness of the application. So, how the arithmetic intensity impacts the optimal configuration. Here we have the core frequency here in the x-axis, while variety of lines are for different uncore frequencies of the CPU. And for very compute-bound region, for workload, we need high core frequency and not so high uncore frequency because it's pure compute-bound workload. The memory subsystem is not so used. Yeah, we have a ratio of dgem matrix vector multiplication and tangents, which is here the compute bound workload. While if we will change the ratio, so we can then see how the curves are changing, we need higher uncore frequencies from the previous 1.6. Now the optimal uncore frequency is 2.2. Well, we can reduce the core frequency from the previous 2.5, if I remember well, to 2.2 and reach lower energy consumption. And yeah, moving forward to the memory bound. So the optimal uncore frequency remains in this case. Yeah, while the optimal core frequency can be lowered, but this is just a simple example of impact of the arithmetic intensity on the optimal configuration of the hardware, while also perform on all the architecture. So yeah, this you've already seen, and another reason why I'm showing it that so this impacts this is written in the hardware, what's the maximum core frequency. But anyway, potentially your application may not reach this configuration because typically there's a power limit of your CPU or GPU also, which for specific arithmetic intensities and in case of Sapphire Rapids, it's way worse than in this slide. So for majority of the workloads, the CPU is running really on the TDP, thermal design power. So then the power capping system reduces automatically the CPU core and core frequency, and it reduces these frequencies to keep the power limit. while not really reflecting what kind of workload it executes. So in this case, we have here the power. So from this is the TDP of that CPU I'm showing. Here at the top, we have core frequency. So for the SSE instruction set, it is running on its maximum. Of the AVX2, it's for that region, also in the SSE. For that region, it reduces the core frequency, but only slightly. In AVX 500, it started to reduce the core frequency. So you can see here we have purely compute-bound workload, but the core frequency is reduced. And here we have the uncore frequency, so the other one. So these frequencies are used really to keep the power at the specified limit, while the configuration of the core and non-core frequency do not have to match what's the optimal. Yeah, that's arithmetic intensity 8. We will focus on this one. So this is the T running on the power limit. The core frequency is on the maximum, while the uncore frequency is reduced to some 2 gigahertz. When having a closer look at that, so if scaling the frequencies, we can see that if we change the configuration, we reduce the core frequency, which creates space for shifting the power to the anchor domain. So increases the anchor frequency to 2.2 gigahertz. Then we have CPU energy savings and also runtime improvement. So this is runtime, the default runtime, that's 1.0, and you can see that for specific anchor frequencies, that's each line for anchor frequency, and for reduced core frequency, that's here 2.1, 1.9 gigahertz. So that this improves the runtime just because it shifts the power from one domain to other. And here's the impact on so this is the default, and you can see the opportunity for the improvement of the CPU energy consumption. So 1.9 core is here, and 2.2 is the green one. So here we are. So energy efficiency improvement. Yeah. The easiest way how to potentially improve the energy efficiency of your application once you're done with improving the performance, which is always the first step, how to improve the energy efficiency. So potentially changing the frequency of the hardware statically. Despite it's not possible to do the frequency tuning in the runtime of HPC systems. Some allows you to change the configuration through the SLARM. So that's also the case of the Marenstrom. Or if it's possible to do the changes in the runtime, then it can be done using a runtime system. And yeah, so statically for the whole application runtime, single configuration, and you see obviously impact on the runtime because you're removing some resources. So then the typical insight to the application is the energy and energy efficiency metric, and looking at the performance degradation, looking what's the configuration of the hardware if we impact the application runtime about some, let's say, predefined limit, what energy savings are available. So that's with the static, while the applications typically behave dynamically, have different requirements on the hardware during the runtime. So one part of the code is compute bound, a different one is memory bound, and already 10 years ago, more than 10 years ago, there was a project, Horizon 2020 project, Redx, building on this idea that we're supposed to split the application into those regions and identify the optimal configuration for each of them to reach the maximum savings. So not only the static tuning, but we call it dynamic tuning. So yeah, a bit blurry, but doesn't matter. Having an example of an application where we have regions for the so-called significant regions, which are, let's say, long enough to allow hardware to change the configuration. We identify what's the optimum, and for each of those regions, the configuration is set. So for this simple lattice Boltzmann example case, it has these two regions. Collide is compute bound, while propagate region is memory bound. And if having the static tuning, because these regions are so different, it's impossible really to find any energy efficiency improvement or energy consumption improvement in this case without impacting the application runtime. So there were some 8% of energy reduction, while the runtime was impacted about 12%. However, if the frequency is C's, both of them, in this case, core and non-core again, these are switched for each region to fit what's the really optimum for each of them. Then the energy was reduced about 20% with very small runtime penalty. So you can see for the computer bound region, this is time it's switched. So here we have the anchor frequency. So the anchor frequency do not have any impact on the runtime for the compute bound region. So it can be reduced, while obviously for the memory bound region, the anchor frequency is very important, while the core frequency has impact, but not so large. So now I would like to finally speak about MERIC, which is a tool we developed. We already started the development under the Redx project, and we are still working on improvement and further enhancement of this tool. So it was designed really to perform, to work as a runtime system. So it means automatic scaling of the hardware parameters to provide energy savings, while we adjusted that to provide not only the automatic optimization without having insight what's really going in the background, No, it also provides the energy efficiency analysis, so tracing of an application, providing not only energy measurement, but also some additional metrics, which gives the insight how the application uses really the hardware. So it's for the C, C++, Fortran, and hopefully soon to be also Python applications. We have first version of the Python, but not yet fully working. For applications with MPI, OpenMP, CUDA, yeah, I'm missing HIP here, running in a variety of hardware platforms where the support of the platforms really mean support for energy measurement in that platform. If there are specific interfaces for hardware tuning, then support for them, and also presenting the performance metrics, that the energy efficiency metrics. MERIC as the basic way how you can use it is the energy measurement. So something that is not typically available through a single interface. Here it is. So there's a command line application, MERIC static, where you provide what kind of power monitoring system you want to use, and then here you have application and the application parameters. So it wraps the application. Once the application ends, you execute the application again, the tool again with the eval parameter. I see that PowerPoint ate one of my dashes, so that there's eval, dash eval. And yeah, then it prints what's the energy consumption, runtime, and the energy consumption. It doesn't have to be just RAPL, it can be several power monitoring systems at the same time. First, this case is for, let's say, single node, while for multiple nodes, we need srun or MPI run to start monitoring in all the nodes. Variety of hardware platforms, variety of power monitoring systems, which we supposed to use. So here it is the current status in the Euro HPC systems. So AMD CPUs, and majority of them, each providing a slightly different interface, how to measure the energy. So you are potentially able to monitor the energy consumption without the MERIC. However, in each machine, you must know how to, which interface you're supposed to use. So in Mariner Storm 5, that's Intel CPUs reading the perf, and NVIDIA GPUs with NVML. So yeah, however, how should I know when I'm in the machine really? So there's another utility part of the MERIC which provides us information about the hardware. So what CPU is there, what GPU, what frequencies are available, whether the MERIC itself is able to change the core frequency, potentially also uncore frequency, if MERIC has access to that information. And here's the critical information we are looking now. That's the power monitoring systems available. So we see that we may use RAPL, in this example, HDIMM, or NVML, HVMON, or something else. So it really depends on the system where we are. So when using MERIC in the POP, when requesting energy efficiency analysis without any hardware parameters tuning, then you should have, let's say, at least subset of these, but if available, all of these metrics. So the performance evaluation to express the energy efficiency, so obviously also the energy consumption measurement. Then what's the carbon footprint of your execution? Based on the location of the system you are using for the analysis. Vectorization ratio, typically very important for the, especially Intel's CPUs, but not only. In ARM machines, this is also very important. The frequencies, on what frequency the application is really running, whether the power capping system reduces the frequency and or not. The memory bandwidth, computational intensity, so are roughly the arithmetic intensity of the executed workload, power consumption timeline, so how the power consumption changes in time, and this can be done in a variety of hardware platforms, obviously with variety of power monitoring systems, but we compare which of them is better to use. So, for example, if staying just in the Mare Nostrum, potentially it can be comparison whether the HBM partition, which is available, brings not only performance improvement, but also how it impacts the application energy usage, because the HBM itself is typically power hungry. So I'm running out of time, but I have very few slides at the end. If we are able to do some tuning in the machine, which is available, for example, in the Deucalion in Portugal. So then we proceed with the application instrumentation, comparing the default application runtime with the runtime when the hardware configuration changes. What's the impact of the frequency scaling on the application regions? And yeah, potentially also evaluating how the power limit impacts the application. Once doing insight to the application, we instrument. So this is the simple API where we identify where those regions. And then using the environment variables, MERIC measurement, RAPL, MERIC frequency, we specify the configuration of the application or the hardware and the MERIC itself. This was for, in this slide, this is for a simple application run, while when doing state space search of what's really the best configuration, then we have another utility which performs the identification of the optimal configuration. Then we have the output files providing not only the runtime and energy, but also the energy efficiency metrics I presented. So we have a PyQt application, radar visualizer, which gives insight to the application, especially comparing variety of configurations of the hardware, how it impacts the application runtime. And yeah, that's it from myself.
Okay, so short review. So you have been introduced to a variety of tools, some of which you may already have known about, or maybe some you discovered during this workshop. The idea, of course, is that this allowed you to see that some tools have focus on different aspects on the performance analysis, be it core level, parallelization, or more complex case like energy, like we just saw. And of course, these various tools may either provide a global view or try focusing on a specific issue. The idea of the workshop is to make you aware of all these tools. We, of course, don't expect you to have become an expert in using all of the tools here, but the idea is that hopefully now you have a better idea of the various tools at your disposal and when you may want to use either of them, depending on the issue you want to tackle, which you may prefer to use, and which are available for the platform you are using, of course. So just another idea how all these tools integrate in your development chain. You will first want to make sure that your application works correctly, of course. So for that, you can use debuggers. And this morning, we saw additional correctness checking tools that will allow you to check that your application is correctly not have any additional hidden bugs. Then you will have to get an overview of the general performance of your application, where you are spending time. So for that, you can use a profiler like Scorpy or Macao and try different parallelization configuration. After that, you may want to focus on the various issues tied to parallelization, and of course, want to know whether you are correctly using parallelization. So if you are in strong scalability, you expect time to decrease as you increase the number of threads and processes. Otherwise, if you are using weak scaling, you simply hope to have a consistent duration of your application, but you increase the size of your data. And of course, after that, you will want to monitor whether communications and load balancing is correctly handled. So for this, you can use the various tools like ScalaSCA and the BSC tool suite, Power Mass X-Ray, to investigate more in detail what happened in the parallelization. Vampire also allows you to analyze all of this. And of course, you may want to make sure that the core computations are correctly used. So you can investigate hardware counters. You can also check that the code generation was correctly performed by the compiler using, for instance, Macao. You can simply make sure that your compiler did the right job. Usually, the compiler is usually your best optimization tool, but you have to know how to use it correctly. And so I think you already saw this graph at the beginning of the workshop. So now hopefully you get a better view on which each of the tool take place in this workflow. So finally, you will soon receive, I guess, an evaluation form. So I know that in these days and age, you are asked to evaluate the quality of basically anything you do. Whenever you so much as open a door, somebody will ask you if you can fill a satisfaction evaluation form on the quality of the handle. But this is really useful to us, actually, because it allows us, one, to know how you appreciated this workshop and possibly to improve it, the overall format of the workshop in the future. And of course, individually for each tool developers, it allows us to get some insight on what you liked and didn't like or want to see improved for each of our tools. So please return this evaluation, and also in this time you also possibly you will also be able to provide insight on what you think of the POP methodologies. And of course, concerning each individual tool, you got the contact for each of the instructors in this workshop. So hopefully in the future, you will keep working on some of the tools, and we welcome any reports, feature requests, bug report, questions on how to use them. This helps us to improve our tool.